Hi everybody, welcome. I just wanted to talk a little bit about redox. First, we're going to go over assigning oxidation numbers, just like we did in class. And then we're going to talk about looking at oxidation and reduction separately. So the first thing we have to be able to do when we're looking at redox equations is be able to assign oxidation numbers. So if I look here, there are going to be 4 rules for assigning oxidation numbers, okay? So the first one is any element in its elemental form, even if it's diatomic, is going to have an oxidation number of 0. The second rule is that hydrogen, like most of your alkali metals, is going to have a charge of +1. The exception of this rule is whenever we're dealing with a metal hydride, for example, sodium hydride. In that case, the alkali metal is going to take the +1 oxidation number, and hydrogen is going to take the -1 oxidation number. That's an exception to the rule. 99% of the time, in a compound, hydrogen will have an oxidation number of +1. Looking at the third rule, oxygen in a compound is generally going to have an oxidation number of -2. The exception is hydrogen peroxide, H2O2. Just remember that it's -1 to cancel out hydrogen's +1. Other than that, in a compound, oxygen should be -2. And the last rule is that unless otherwise specified, so looking at this polyatomic ion here, this rule does not take account, but most of the time positive will cancel out negative when you're assigning oxidation numbers within a compound, okay? So for example, up here, hydrogen, for number 1, is going to have a +1 charge. Therefore, chloride would need to have a -1 charge to cancel it out. Looking at this, however, this polyatomic ion, my charges aren't going to completely cancel out. If I use the rules, oxygen is going to have a -2 charge, so that means I've got 2 negatives there, and hydrogen is going to have a +1 charge. Not all of my negatives were canceled out by positives. There was 1 negative left over, which explains the charge on the hydroxide ion. Okay, so that's assigning oxidation numbers. That's really important whenever we get into redox reactions. What we're going to do is we're going to look at a redox reaction. We are going to assign oxidation numbers and determine what was oxidized and what was reduced. And then we're going to sort of break the equation into the oxidation half and the reduction half. Okay, so looking at number 1 on the back of that first page of your packet, if I were to assign oxidation numbers using the rules, these diatomic elements here would each get the oxidation number of 0. And when they're combined in a compound, oxygen gets the -2 oxidation number and hydrogen is +1. Okay? I need to figure out what was oxidized and what was reduced. So remember oil rig, oxidation is losing and reduction is gaining. If I look at hydrogen, it went from 0 to +1. So each hydrogen was losing 1 negative electron. If it was losing electron, then it was oxidized. Oxygen, on the other hand, went from a 0 oxidation number to -2, which means it became more negative because it gained electrons, and that means it was reduced. And it may seem kind of weird that it gained electrons but was reduced, but we're thinking about the oxidation number here. It went from 0 to -2, which on a number line would be movement in the negative direction. It would be reduced, okay? So now comes the time for me to sort of break this up, okay? And what am I starting with? I'm going to start with the oxidation part of this. My 2 diatomic hydrogen molecules broke apart and formed 4 positive hydrogen ions. They aren't really ionic because this is a covalent compound, but when we're assigning these oxidation numbers, we're pretending that everything has a charge, okay? So what I did was I made 4 hydrogen ions, 4 hydrogens with that oxidation number of +1. In the process, each hydrogen lost an electron. And anytime something is lost, it's going to end up part of the products because it's leaving the reaction. So those hydrogens were complete, but now they've broken up into 4 hydrogen ions and the 4 electrons that were lost. Okay? The next part of this is that I had a diatomic oxygen molecule, and each oxygen gained 2 electrons. There were 2 oxygens, so think about it mathematically. If I had 2 oxygens and each oxygen gained 2 electrons, that's 4 electrons being gained overall. And it makes 2 oxygen ions with an oxidation number of -2. Okay? Now the law of conservation of matter comes into play here. So whatever number of electrons was lost needs to be the same as the number of electrons being gained. Otherwise, you need to go back to your equation and analyze whether or not it was balanced. The number of electrons should cancel each other out, just like we have the same number of hydrogens on both sides of the equation and the same number of oxygens on both sides of the equation. So make sure that those things cancel out. If not, again, look back and see if it needs to be balanced. Okay? Let me look at number 2 with you. So looking at number 2, the charges are already done for me. The elements that are by themselves get an oxidation number of 0, but that iron is going to become a +2 ion, and the zinc is going from a +2 ion to a neutral atom. So let me think about it for a second. Iron's going from 0 to +2, it's losing 2 electrons. So this is the oxidation part of my reaction. And if zinc is going from a positive charge to a 0 charge, to a 0 oxidation number, it's actually moving backwards on the number line, so it is reduced. So what would my half equations look like? I have iron becoming iron with a charge of 2+, and in the process losing 2 electrons, so that should be part of the products. On the other side, I see zinc with a positive charge gaining 2 electrons to become a neutral zinc atom. So that's it. That's what you do. You simply take the equation, assign oxidation numbers, figure out what was oxidized, pull that out, and make that a half equation, and then figure out what was reduced and pull that out and make that a half equation. And we'll work on it some more, but this is the basic process. Okay, have a good night.